I kind of grade in a hurry, so. But no, there is a relatively easy way to do that problem. The way I have in my solution, it's like 3 pages long. That can be vastly shortened. If you multiply by EIJ on one side and you multiply by EIJ on the other side, if you study what that means, and it's in my notes, multiplication by the matrix unit, what it does is it zeroes out everything and it puts like the ith column in the jth column. And when you multiply on the other side, it like puts the ith row in the jth row, or vice versa. So what you end up with is an equality where everything is 0 except for like the ith column and the ith row or something like that. And if you just equate those two things, you can easily show that any non-diagonal entry is 0 and that the diagonal entries have to be equal. And that then gives you that the matrices which commute with all other square matrices are of the same size, are just multiples of the identity, which one of you guessed because, well, we talked about it, but I also mentioned that that was an answer, but it was an answer that also needed to be explained. And you know that. So anyway, where's my, oh man, did I not? Oh, there it is. Let me begin with a word of prayer before I waste more class time here. Dear Father, we thank you for this day. Again, I thank you for these students and just ask you just bless our work today. Help us to glorify you what we do and just understand a little bit more about linear algebra, Lord. In your name I pray, Lord Jesus. Amen. So we have made it all the way to chapter 3. I probably should post like a little video about section 2.6, which I failed to get to last time. My bad. Sorry about that. I have edited the notes, so I'm about to post like the final edit, hopefully. And in that final edit, I have added an appendix about like functions, and like what we mean by a set of like a function acting on a set, or the inverse image of a set under a function, all that stuff, injective, surjective, bijective, what we mean by those words if you've forgotten. So I will have an appendix like that posted in the new version of the notes. So that's upcoming. But today we're talking about linear transformations. So properly speaking, linear algebra is the study of linear transformations, right? Vector spaces on their lonesome aren't really that interesting. What's more interesting is, mappings from one vector space to another, and that's what a linear transformation is. Moreover, the concept of a linear transformation is it's really important to more than just linear algebra. Like oftentimes in science and engineering and mathematics, we have some kind of nonlinear thing, right? But we replace it with a linearization. And so in that sense, linear algebra appears like everywhere. So here we go. So we're going to let V and W be vector spaces over a field for this whole discussion, all right? So V and W, vector spaces over field F, all right? So definition, if we have a function t mapping from V to W, satisfying additivity, so t of x plus y is t of x plus t of y, and homogeneity, t of cx is equal to c t of x. All right. So this is, for all x and y in V, for all x in V, and c in the field. All right. Then we say T is a linear transformation. Or if we get sick of writing transformation, we might write trans, but we don't like to say that anymore, so we'll probably say or map. All right. So transformation, function, map, these words are kind of used interchangeably around here. T is an element of script L, like this script L, okay? VW. So this guy right here is the set of all linear transformations from V to W, all right? We also write, if T is an element of the linear transformations from V to V, we'll also call that just L of V, or why have one notation or two notations when you can have three, and V. So such a thing is called an endomorphism, which is a fancy way of saying a linear transformation from a vector space back to the same vector space, all right? We'll spend a fair amount of time in here studying endomorphisms as time goes on in here, all right? So what are some examples of linear transformations? Well, let's look at them. So example 1. If I have f which goes from the reals to the reals, and it's defined by f of x is equal to mx plus b, then f is not an element of the linear transformations on R if b is not equal to 0. So we can prove that a linear function is not a linear function unless b is equal to 0. Let me give you a simple way to prove that. Like, here's a fundamental theorem about linear transformations. So let's do this theorem, which will help us with example 1. So here's the theorem. If you've got T is a linear transformation from V to W, then T of 0 is equal to 0. How do we prove this? Any ideas? How about this? So proof goes like this. T of 0 is equal to T of 0 plus 0, right? Because 0 is equal to 0 plus 0. But by additivity, this is equal to T of 0 plus T of 0. Hence, T of 0 is equal to 0. Because I can subtract T of 0 from both sides, right? So 0 has to map to 0 for a linear transformation. Quick way to check if something's a linear transformation or not is, does it map 0 to 0? If it doesn't, game over, it's not a linear transformation. And that's why I can easily see in example 1 that if b is not equal to 0, right? If I plug in f of 0, what's f of 0 equal to? It's the y-intercept, right? It's b. Okay? All right. Example 2. Example number 2. I'm going to bump it up a notch here. We'll go f a mapping from Rn to R, and I'll define it by this. F of R is equal to R dot R. All right, R. So in the notes I have, like, for the two-dimensional formula. I'm going to bump it up a notch here. N-dimensional. Is this linear? Well, let's start out by checking 0. Does 0 map to 0? Is 0 dot product 0, 0? Well, sure enough it is. But is that enough? Well, that's not enough. We need to check what? Additivity, sure. We could try that. How about, what if we check out like f of c times r? How does that go? So c, so I'm ignoring you, Gideon, sorry. I mean, I don't disagree with you. Additivity is another way we could show that it's not a linear transformation, but that would require me more mental energy. It's easier to see this, see, because like cr dot cr is what? C squared r dot r, right? By properties of the dot product, which is c squared f of r. So we don't have homogeneity. We don't have item, part 2 of the definition. So, okay, so yeah, thus f is not linear. It's not a linear transformation from Rn to R. Okay, it's something else. Yep. Oh, yes, thank you. Still in the marker. There we go. Muchas gracias. It's because I'm teaching this class at 8:15 I make these kind of mistakes. Oh, wait a minute. Yes, sir. I can't use that I can't use that excuse here, can I?
Actually, you can, because 3's half an 8 and it still starts at 15.
Sure.
Interesting. Let's see here. Let me move on. All right, so let me start giving some positive examples, yeah? Example 3, how about this? We could look at, I'm going to use S rather than T here. S, a linear transformation from F m by n to F n by m, where we're just going to say S of A is equal to A transpose, right? That is a linear transformation because you guys proved the properties of the transpose, right? Which is to say that this is a linear transformation, right? I mean, we've got S of A plus B transpose, properties of the transpose, A transpose plus B transpose. I'll throw a constant in here for good measure. Same song and dance, right? We can check linearity all at once in one foul swoop rather than subdividing up parts 1 and 2. We can do part 1 and 2 at once by looking at a linear combination rather than just a sum or a scalar multiple, right? Take C equals to 1, we get additive. Take B equals to 0, we get the homogeneity we want. So there's that. Other kind of general examples. So these work for any vector space. If we take T of 0, T of x is equal to 0 for all x in V, or if we let me call it T1, and we take T2 of x equals to x for all x in V, right? Then in that context, we call, in that context we call T1 the zero transformation, right? The zero transformation, and T2 is the so-called identity on V, all right? So these are both endomorphisms on a vector space that are always there, the trivial transformation and the identity transformation. Another example is integration. So we could say T is a mapping from the continuous functions over the reals to the reals, all right? And so we could say L of F is by definition the integral from 0 to 1 of f of x dx. This makes sense because you guys have had calculus 1 and you know that the integral of a continuous function exists, right? And by properties of the definite integral, that's additive, and you can pull out a constant, right? So it is a linear transformation. What is another calculus-based thing you could do? If you had, say, from the once continuously differentiable functions to the reals, maybe not to the reals, but to the, let me just be lazy here. What's C infinity R? So I'll tell you, C infinity R, these are the set of smooth functions on R, right? So if I take the derivative of a smooth function, I get another smooth function. The derivative of the sum is the sum of the derivatives, and you can pull a constant out, right? So that's a linear transformation. And we could go from here, right? What if you had a function of n variables, right? If you had a function of n variables, you could talk about the nth partial derivative being a linear transformation on such functions, right? If you had the smooth functions of n variables, you could take partial derivatives. That would be a linear transformation. All right. So I already showed you the first basic theoretical thing about linear transformations, which is that 0 maps to 0. What do you think a linear transformation is going to do to a linear combination? So, proposition 3.1.12, we have L an element of the linear transformations from V to W. And point number 1, L of 0 equals to 0. Point number 2, L of a linear combination, sum I equals 1 to n, let's say, of Ci Vi, is the sum I equals 1 to n of Ci L of Vi. Now I have used just plus dot dot notation in the notes, but there you go. All right, so we already proved 1. How should we prove 2? And this is true for all n in the natural numbers. That's kind of a giveaway, isn't it? How do we prove something for all n in the natural numbers? We do what? Induction. Right, so let's prove 2. Let's look at the proof of 2. How does it go? So proceed by induction on n. So L of the sum I equals 1 to 1 of Ci Vi is by definition L of C1 V1, which is C1 L of V1, which is the sum I equals 1 to 1 of CIL VI, right? So thus n equals 1 true. That was supposed to be true. But my red marker's dying. If I can find another one. Okay. So suppose inductively it's true for n. Suppose that, let me just, I don't want to write it again. Suppose star is true. Consider L of the sum I equals 1 to n plus 1 of Ci Vi. All right, so by definition, that's L of Cn plus 1 Vn plus 1, right? Plus the sum I equals 1 to n of Ci Vi, right? By definition of sum. Then what can I do? I can use additivity of the linear transformation, right? So this gives me L of Cn plus 1 Vn plus 1 plus L of the sum I equals 1 to n of Ci Vi. But then I can use homogeneity to pull out the Cn plus 1. And then I've got L of Vn plus 1, right? But I can also use the induction hypothesis on the other piece to get the sum I equals 1 to n of Ci L of Vi. So this is by homogeneity, by 2, by L, a linear transformation, and the n star, right? Which is what I've labeled my induction claim here. Then what? Then we simply apply the definition of the finite sum another time. See, this is then equal to the sum I equals 1 to n plus 1 of Ci L of Vi, right? And then, so that's it. Hence, star true for all n in the natural numbers, by proof by mathematical induction, also known as PMI. This is a conclusion that should appear at the end of induction proofs. Some of you think that you've reached the place in your life where you don't have to write conclusions to your proofs. This is not the case. I will take your points. I'm not taking them on homework because, well, then I'd have to like find a finer grain. I just don't think I've taken points on homework for this yet. But like on a test, something will happen if you don't conclude proofs, right? It's not enough to give an argument. You must conclude the argument. This is important, you know? Otherwise, I don't know if the story's done. You know, it's like the end credits have to roll in a movie at some point. You know, otherwise you never watched it. That's not really true. I could find a better analogy. That's your job. I'll make that homework. I don't know, but write your conclusions. Why do you guys hate writing so much? Anyway, you know who you are. Where was I? Okay, so that's that. Proposition next. Next proposition. Let me erase some of this here. Suppose you have a linearly dependent set. What do you think a linear transformation does to a linearly dependent set? Proposition. Let L be a linear transformation from V to W, and S a linearly dependent subset of V, right? Here's the conclusion. Then L of S, all right, is linearly dependent. All right. So here's the deal. So suppose Vj is equal to, you know, well, I guess we don't have to do V. We'd say suppose V is equal to a sum, you know, I equals 1 to whatever k, let's say, of Ci Vi for, you know, Vi comma V in S, right? This is possible because, why? We're assuming S is linearly dependent, so a linear dependence must exist. So this is the linear dependence. I'm writing one of the vectors in S as a linear combination of the others, right? Then L of V is equal to what? Well, L of V is equal to L of this sum, yeah? But what did we just prove? We just proved that the definition of linearity extends past two things to as many things as you like, right? In other words, we can pull the finite sum out. And what do you got? What is this?
Linear combination.
Right, so this right here is a linear dependence in L of S. What is L of S? What's that mean? L of S is the function L applied to all of the things in S. It is a set of things. So by definition, this means L of X such that X is in S. That's all this means, all right? It is a set of elements. Yeah.
Do you have to, or can you assume that L of S is a subset if S
Is L of S a subset? Well, L of S is automatically a subset. That is true because L maps from V to W. So the output's L of X. These have to be in W, right? So this is a subset of W. Now I didn't say that S was a subspace. But the question you might be thinking about is what if we were feeding a linear transformation a subspace? Is it the case that the image of a subspace is a subspace? That's an interesting question to ask. We should figure that one out. One thing at a time, though. So there you go. A linear dependence is mapped to a linear dependence under a linear transformation. Simple as that. Now we need to introduce a couple of important players in this game, namely the kernel and the image. So here's the kernel definition. For T, a linear transformation from V to W, we define kernel of T is equal to x in V such that T of x is equal to 0. In contrast, the image of T, also known as the range of T, is equal to T of V such that V is in V. Right? Now, let me just make a comment here. Once you read the appendix, or if you remember your Math 200, you maybe recognize that what we're talking about here is the inverse image of the set just containing 0. This is all of the things which map to 0. That's the kernel. On the other hand, the range is simply the image of the domain under T. It's TV, or T of V. All right? The things I just wrote are defined by the things I already wrote. All right, so. So here, while I'm erasing, you guys tell me, what would the kernel of the derivative map be if we were looking at like all polynomials? Remember, we just talked about the derivative map. It's a linear transformation, right? It's still a linear transformation if we think about the set of polynomials, right? The derivative of a polynomial is a polynomial. We agree? What's the kernel of the derivative map on polynomials?
Is that all constant functions?
All constant functions, exactly. Very good. So there would be an example of a kernel. What's the kernel of the second derivative?
All linear functions?
All linear functions, that's right. Yep. So what is the significance of the kernel? Well, this kernel is very significant. Here's one of its main features, theorem. All right, here we go. T from V to W is an injective linear transformation if and only if the kernel of T is just equal to 0. So if this is not clear, we're assuming that T is linear from the outset, okay? So we're saying that linear maps are injective, they're one-to-one, if and only if the kernel is 0. All right? So let's look at the proof of this thing. Suppose T is an element of the linear transformations from V to W. That's a precondition, so we'll put that up there, okay? Now let's go this way. Assume T is 1 to 1, all right? Let X be an element of the kernel of T. What does that mean? T of X is equal to 0, right? But what else do we know? We already proved this today. 0 is equal to T of what? T of 0. What does it mean to be 1-to-1? two outputs are equal, the inputs have to be equal, right? So 1 to 1 tells me this equal to that, implies x is equal to 0. Hence, you know, the kernel of t is equal to the set containing 0, because I just showed you that an arbitrary element in the kernel is just 0. And we know 0 is in there because t of 0 is 0. Are we good? Did I go too fast? I can talk slower. I shouldn't make offers I don't intend to honor. You can watch it back at half speed. No? Okay, so how about the other direction? Suppose the kernel of t is the set just containing 0, right? We'd like to show t is 1 to 1. All right? How should we do that? Let x and y be in V, and suppose that t of x is equal to t of y. Right? Then what? Well, then t of x minus t of y is equal to 0, and so t of x minus y is equal to 0. But what does that mean? Well, that means that x minus y is in the kernel because it maps to 0. But the kernel is just the set containing 0. Therefore, x minus y has to be equal to 0, which tells me, of course, x is equal to y, which tells me that t is injective. And so this is a biconditional proof. We proved the forward and the converse, so we've done it. So is a linear transformation 1 to 1? All you have to do, calculate the kernel. If the kernel is 0, it's 1 to 1. If it's not, it's not. Simple as that. So what the linear transformation does at 0 forces the behavior everywhere else. This is so special to linear transformations. Let me show you an example outside of the realm of linear algebra where this doesn't happen. So like example, what am I on? Example what? 6, 7? 7. All right, so check this out, right? So if I look at like f of x equals to x squared, well, the inverse image of 0 is just 0 here. But the inverse image of c is minus root c and plus root c, supposing that c is positive. If c is negative, the inverse image is empty. So like the size, what I'm trying to say here is, well, I mean, just to the point, the kernel, quote unquote, of this map is 0, and yet it's not 1 to 1. See, because like f of plus or minus root c both map to c, right? So this is not injective, even though the kernel is 0. Something very special happens for linear maps where what happens at 0 has to happen everywhere because the additivity transfers the behavior everywhere. Anyway, we should think more about this, but I'll just say that for now. All right, so let's get back to Sam's question, which is theorem 3.1.17. Sam, did you read ahead? No. Okay. But were you thinking S was a subspace because it was S? That's a popular misnomer. You know, like S must be for subspace, but S is just a letter that I used. Someone once told me at the end of linear algebra that my letters meant absolutely nothing. I took it as the highest praise. So, no, but we do use every different letter, every different which way. So, like context matters. You have to, that's why we have to announce where things are in here. All right. Okay, so here's the deal. T, a linear transformation from V to W. All right. Number one. This is a theorem. If V naught is a subspace of V, then T of V naught is a subspace of W. And two, if W naught is a subspace of W, then the inverse image under T of W naught is a subspace of V. Now Sam might be like, I didn't ask for that one. Well, it's too bad. You're getting both of them. How should we prove these assertions? What do you guys think? What's going to be involved? So what should be involved is the fact that they're subspaces and the fact that T is given to be a linear transformation. That should be pretty much it. And so the way to prove these sorts of things is to apply the subspace test and work through the definitions. Let's do part one. So for one, let's let x and y be elements of T of V naught. And let's let C be in the field. All right? Then what? Then there exists, let's say, A comma B in V naught such that what? T of A is equal to X and T of B is equal to Y, right? That's what the image of V naught means. It's the set of all outputs from V naught. So to say X and Y are in T of V naught is to say that there's some inputs, A and B, which map prospectively to X and Y. So this A and B have to exist, right? So observe that T of CA plus B is equal to C times T of A plus T of B, right? Which is equal to CX plus Y. But what does this mean? And CA plus B is an element of V naught since V naught, well, since A and B are given to the elements of V naught, right? And V naught is a subspace of V, right? Rather than saying and, let me say note. Note. Note this. Right? So what I'm showing you is that this vector right here is in V naught. What's that mean? That means that this guy right here is the image of something in V naught. Therefore, Cx plus y is an element of T of V naught. And then we could say, thus by the subspace test, it's a subspace. And then I would take off 10% credit. Why? What does the subspace test demand of us?
You have to prove zeros of it?
We have to prove it's non-empty, right? Zero?
Yeah.
Great, okay, good. T of zero is what? Yeah, use zero, right? T of zero is zero, therefore zero is in the image. So, and as, you know, 0 is an element of T of V naught, since 0 is an element of V naught, and T of 0 is equal to 0 is an element of T of V naught, right? Hence, T of V naught is a subspace of a W. So that's how the proof of 1 goes. There are probably other ways to formulate this proof, but this is the way that's natural to me personally. How about 2? How do we prove that? So to prove 2, pretty much the same song and dance here. I would for 2, I would let, x and y be elements of, or I mean, you could do x1 and x2 if you want. Let me do that. Let me try a different notation for this one. Let's let y1 and y2, my bad. Let's let x1 and x2 be in the inverse image of W naught and C be in the field. Then what do we do? Then what that means is that T of x1 and T of x2 are where?
B naught or B? Wait, no.
We're in part 2.
Oh. W.
Yeah, these are in W naught. So the inverse image of W naught, it's all things in the domain which map into W naught. But then what? T of Cx1, well, Cx1 plus x2 is equal to Ct of x1 plus T of x2, right? And hence what? Cx1 plus x2. Now, I guess I'm missing something here. What can I say about this right here? This is an element of W naught, right? Which is a subspace of W. Why can I say that? Because T of x1 and T of x2 are in the subspace, which is closed under linear combinations by definition of subspace, right? So this is in W naught, but this being in W naught means that this input for T is in the inverse image of W naught. So hence Cx1 plus x2 is in the element of T inverse of W naught. Which is what we want to show. Because now we've shown that given 2 points in the inverse image, a linear combination of said points are in the inverse image. Hence, I can apply the subspace test. I do need it's not empty. What do I use for showing it's not empty?
0.
0?
It's T of 0 equals 0, meaning
right.
the inverse applies as well.
Yeah, I guess I probably should have said that up here, By the way, 0 is an element of T inverses W naught, which is not equal to 0. Okay, it's not empty anyway. So, all right, anyway, so the point is, this is a subspace of V by the subspace test. Corollary, kernel's a subspace. Because the kernel is the inverse image of the 0 space, which is a subspace. And the inverse image of a subspace is a subspace. Therefore, the kernel is a subspace. Likewise, the image, the range is a subspace by part 1, special case. So kernel and range are kind of extreme examples of this theorem. But linear transformations, and they take linear stuff to linear stuff. Notice that the inverse map there, it does not exist as a function, generally speaking. All right, when I use inverse image in here, like I did here, all right, I am not saying that the map T is invertible. This is inverse image as a function. Not as a function, but as a set, you know? So when is the function invertible? Only if it's both one-to-one and onto, right? And there's lots of functions that are one-to-one but not onto. Okay? So, so let's talk about a special case. Well, all right, I guess I'll just continue on here. So what can you tell me about new linear transformations from old? Like, suppose I have two linear transformations and I add them. What do you get? A linear transformation. What if I have a scalar multiple of a linear transformation? Like 3 times a linear transformation. Is it still a linear transformation? Sure enough. And we can prove those by just examining the axioms, right? So like theorem, if let's say S and T are in the linear transformations from V to W, then C times S, right, and S plus T are in the linear transformations from V to W. All right? Ooh, what does this mean?
Linear transfer measures are a vector space.
Yeah, but why? Of what context? Like, what are they a subspace of?
Subspace of functions mapping V to W.
Right. So exactly, we see the linear transformations from V to W are themselves a subspace of the function space from V to W, which we already know is a vector space. That's in our big list. And this theorem establishes the subspace test for linear transformations. Why is it not empty? We already know the zero transformation is a transformation from V to W, right? So it's non-empty because it's got the zero transformation. So yes, it is a vector space on its own right. A kind of big, scary vector space, but a vector space nonetheless. Yeah? But there's more. There is more. And the proof of this, guys, is on page 86. I have the gory details of this theorem on page 86. They're not especially exciting, so I won't put them on the board here. This one's a little more interesting. I'll go through this one. Theorem, if we have, let's say, T, an element of linear transformations from V to U, and S, an element of the linear transformations from V to W, then the composite, we'll write it down and see if it makes sense. S composed with T, is that right? T goes from V to U, oh no, other T composed with S. I'll get it eventually, guys. Does that make sense? S takes the input, V takes it to W, this takes the input. What have I done? Hold on a second.
Do you want S and linear transformations from W to V?
I mean, yeah, fine. You want to do that? I mean, we'll try that. If I do that, then S goes from W to V, and then V goes, okay, great. So the input is in W, it goes to V, then V goes to U. So this should be an element of linear transformations from what? From input to W to output to U. Sorry. Ay, ay, ay.
Should S and T be swapped there?
What?
Should S and T be swapped there?
No, no. I don't believe so. So S inputs from W, it outputs to V, and then that feeds it into T, which takes V to U. Let's work it out. So we have T composed with S, acting on, let's say, Cx plus Y, right? Let X and Y be where? Allegedly in W, and C in the field. If I do that, by definition of composite, this is T of S of Cx plus y. All right? And then what? Well, by linearity of S, this gives us T of Cs of x plus S of y. Notice here that S of x and S of y are where? Where are those in? By construction, those are elements of V, right? Those are the allowed inputs of where? Of T, right? So this makes sense. T is taking inputs from V as we expect. And then we use linearity of T. And we get C times T of S of x plus T of S of y. Which gives me, lo and behold, T of T composed with S of x plus T composed with S of y. Which is exactly what we want to see for the composite to be linear. So the composition of linear transformations is, again, a linear transformation. The sum, the difference, the scalar multiple of linear transformations is a linear transformation. So let's see, I think we've gotten to basically theorem 3.1.25. I'll probably pick up there next time. But what's left to prove here is I want to talk to you guys more about in 221, what kind of linear transformations we talk about? Just the ones of what? Of column vectors, right? So every linear transformation is matrix multiplication by some matrix, right? So I'd like to prove that in general in here, where it can be proved, which is not in general. See, because that integration I wrote is not matrix multiplication. The derivative on polynomials is not matrix multiplication. See, the notion of linear transformation here is far more abstract than what you've been exposed to thus far. All right? So anyway, that's that. So, and we'll have a quiz next class. I wanted to give you guys a kind of heads up. So it should be like an index calculation, and then there should be another one